Okay, so in keeping with the objective and the focus of this this series of videos, which is on exploring different techniques for solving problems in dynamics, with some emphasis on rigid body problems. In this video, what we'll do is we will take one of the problems that we had solved in a prior video, specifically in video 16, and we will just solve the problem using an alternate approach. Specifically in video 16 we had solved the problem using the relations of relative velocity and accelerations, and here we are going to use direct differentiations. So let us solve the problem again with this approach. So the problem in video 16 was that of a disk that is turning about a fixed point with an constant angular velocity of omega, and on that disk there is a tether or a rope that is wrapped, at the end of which there is a mass particle, and the rope wraps or unwraps, and however the rope remains taut. So the length of the rope, which is given by L, so L changes as the rope or tether wraps or unwraps. Rope is always taut. And this is an arbitrary configuration. The disk is of radius small r. We use a rotating frame where the ER unit vector is along the rope and E theta is perpendicular to the rope. Of course, EZ is mutually perpendicular to these two vectors, so it is pointing perpendicular to this sheet of paper, pointing upwards. So the right-handed coordinate system is ER cross E theta gives me EZ. So this is our right-handed coordinate system. To explain how the motion of this particle is happening due to the two effects, that is rotation of the disk and unwrapping of the rope, we can explain that also by considering this Cartesian coordinate frame I and j, or x and y, and if I denote the particle's position as P and the point where the rope is tangential to the disk as Q, center of the disk as C, then an arbitrary configuration of this rope with this disk can be given by a combination of two things. One is the fact that the disk has turned by an angle theta, and on top of that, let's say that the rope has unwrapped by an angle alpha. So this gives a general configuration of the rope and the disk assembly. And the goal of this problem has been to find the velocity and acceleration of the point P. So find velocity and acceleration of P. So this has been the problem, and just in the interest of time, without going into the details, one of the results that we found, this is something that we found when we solved the same problem but using relative velocity and acceleration, was that the net angular velocity, so net angular velocity of rope is given by the vector omega, which is alpha dot plus theta dot Ez. So it's in the z direction. So let me just show the Ez direction here. And we have derived this to be equal to L dot over R plus this capital omega Ez. So keep in mind that since L is changing due to the wrapping and unwrapping, so there is an L dot, and it's that L dot and R that determines the rate at which this angle alpha is changing due to the wrapping and unwrapping. So the net angular velocity of the rope is due to the contribution of two things. One is the rotation of the disk, and the other is the wrapping and unwrapping of this taut rope. So this was an angular velocity expression that we had calculated in our previous approach when we solved this problem. Let me just clarify that this is going to be solved using direct differentiation. Okay, so now even in direct differentiation, as we shall show, there are actually two different ways of doing it. So the first is method 1, where we'll say that the position of P, position of the particle at P, that is Cp, C is considered to be a fixed point, is given by, if you think about it, Cq is in the direction of E theta. So Cq is parallel to E theta, and Qp is in the direction of Er. So therefore the vector Cp is R E theta plus L Er. Right? And so therefore velocity is given by nothing but the differentiation of this vector. It's quite simple actually. So this is R E theta dot plus L dot Er plus L Er dot. And you see there are three terms that show up, and that's because even though we are doing direct differentiation, our unit vectors are rotating unit vectors, and so we need to take the derivative of those unit vectors. And among the vector lengths R and L, R is a constant while L is changing, so we have to have that L dot. And so here we have R times omega cross E theta plus L dot Er plus L times omega cross Er. Right? Because we are taking the derivative of unit vectors, so its derivative of a unit vector is the angular velocity, net angular velocity of the unit vector cross the vector itself. So Vp is therefore equal to R times omega cross E theta. So this is my omega, it is in the direction of Ez. So when we do this cross product, it is going to be Ez cross E theta, which is going to be negative Er. So we will have negative L dot over R plus omega ER plus L dot ER plus L times, and now omega cross ER. So omega has EZ in it. So when we do EZ cross ER, we get E theta. So no change in sign. So L dot over R plus capital omega E theta. Right. So at this point, we can just simplify the expression. And upon simplifying, what we have is the following. We have negative L dot negative R capital omega plus L dot ER plus L times L dot over R plus omega E theta. So we have a cancellation here, and we end up with negative R capital omega ER plus L times L dot over R plus capital omega E theta. So that's the velocity Vp, and you can verify that indeed using our relative velocity approach also we got the same result. So next we move on to calculating the acceleration, so AP, and here again we are going to use direct differentiation. So we are just going to directly differentiate the velocity. So we'll have negative R omega, both of these are constants, R and omega. So ER dot, so let's write ER dot right, plus we will have L dot times L dot over R plus capital omega E theta plus L times L double dot over R E theta plus L times L dot over R plus omega E theta dot. Right, so here we again insert the unit vectors, or rather the derivative of the unit vectors. So ER dot is, we had found it out when we were deriving the velocity. So let me just take a look. So it is L dot over R plus capital omega E theta plus we have L dot times L dot over R plus omega E theta plus L double dot over R E theta plus this term. Here we have a E theta dot, and we had calculated the E theta dot when calculating the velocity, and so we'll have negative L dot over R plus capital omega squared ER. So that's the expression of the acceleration. So let me just make sure yeah, so at this point what we can do is we can simplify things a little bit. So if you take all the terms, there are three terms here that contain E theta, so I'm just going to put them all together. Minus omega L dot minus R omega squared plus L dot squared over R plus L dot capital omega plus L double dot over R. All these things times E theta minus L times L dot over R plus capital omega square ER. You can see that there is a cancellation that's going to happen, and what we'll be left with is minus r omega squared plus L dot squared over r plus L double dot over r e theta minus L times L dot over r plus omega whole squared er. Let me just check. We will have, yep, indeed. So we have the right expression of the acceleration. So this is method 1, where you see what we have done is, starting with the problem definition, we decided to do the direct differentiation, but our direct differentiation was a little bit different from the traditional differentiation approach that we take, where we express the position usually in the Cartesian coordinates and then do the differentiation. Rather, in this method, what we did is we still expressed the absolute position of the particle P, but we expressed it using the rotating frame er and e theta. And hence what happened is, in the process of calculating the velocity, we had to make sure that these unit vectors were differentiated. And in differentiating these unit vectors, we needed the overall angular velocity of this rotating frame. So those were incorporated, and we found the velocity. Now we went from velocity to acceleration, just continuing that process of differentiation. Here again, what we did is, when differentiating, knowing that these unit vectors are rotating, so we took the derivatives of these unit vectors again, incorporated those derivatives, and then simplified the result to get the final solution. And so this result, you'll see both the acceleration and the velocity, they match with the previous results that we had, where we used the relative velocity approach. Next, what we'll do is we'll do method 2, where in method 2 our approach is going to be to use a Cartesian frame, which means that instead of expressing the position in the rotating frame, we'll express the position in I and j, and then take the derivative, find the velocities, and then of course we will show that our results match with these results by again converting from ij to er, just to show that the results match. So we'll do that next. So here what we do is we so method 2, this uses Cartesian coordinates for position vector. So here you can see that Cp can be given by the x coordinate of P and the y coordinate of P, and the x coordinate of P is nothing but r sine theta plus alpha minus plus L cosine theta plus alpha. Knowing here that by virtue of the fact that this rope is taut, then the rope makes an angle of theta plus alpha with the horizontal. So with that understanding, you can write the position, the x position, the x coordinate rather, with this expression, and the y coordinate similarly is going to be r cosine theta plus alpha plus L sine theta plus alpha. This is in J. Okay, so we'll proceed from here. So therefore Vp is equal to, now when we take the derivative, since I and j over here are fixed in direction, so neither their magnitude, of course because they're unit vectors, nor their directions are changing because these are fixed directions. So when we take the derivative of Cp expressed in I and j, we do not need to differentiate I and j, okay, because their derivatives are 0. So we have minus r cosine of alpha plus theta times alpha dot plus theta dot minus L sine theta plus alpha dot plus theta dot plus L dot cosine of alpha plus theta. This entire expression is in the I direction, and plus in the j direction we have minus r sine theta plus alpha times theta dot plus alpha dot plus L cosine theta plus alpha theta dot plus alpha dot plus L dot sine theta plus alpha, and this is in the j direction. So as you can see, these expressions are getting a bit complicated, and that's just because we are expressing these vectors in the I and j directions, and clearly in the I and j directions the expressions of these vectors are rather long. Now in video 16 we had shown that these unit vectors I and j can be expressed in terms of er and e theta. Well, this is the velocity expression. You can substitute for alpha and theta dot and get the expression, but what we want to do at this point is we want to show that the expression that we have here is exactly the same as the expression that we had with er and e theta as the unit vectors. So in order to do that verification, what we need to do is we need to transform this solution to a vector with er and e theta, so that we can do a direct comparison of the vectors. So in order to do that, you will see that in the previous video, that is video 16, I had shown that I can be expressed as er cosine of alpha plus theta minus e theta sine of alpha plus theta, and similarly the unit vector j can be expressed as er sine alpha plus theta plus e theta cosine of alpha plus theta. So at this point, if we make these substitutions, then we will have Vp in the form of er and e theta. So let's make those substitutions. So therefore Vp is equal to, we take this expression which has a coefficient of I. If we multiply this expression by cosine alpha plus theta, then that's going to be a coefficient of er. So we will have as coefficient of er minus r cosine squared alpha plus theta times alpha dot plus theta dot minus L sine theta plus alpha cosine of theta plus alpha dot plus theta dot plus L dot cosine squared alpha plus theta. So these terms are going to get generated when we substitute for I and we collect the terms that have er as coefficients. Now if we do the same thing in j, that is substitute for j and collect the terms that have er as coefficient, then we will have, what we'll have to do is we'll have to multiply by sine of alpha plus theta, so minus r sine squared alpha plus theta, alpha dot plus theta dot, plus L cosine alpha plus theta sine alpha plus theta, theta dot plus alpha dot, plus L dot sine squared alpha plus theta. Now this is going to have ER as the coefficient. A couple of things can be immediately seen. So for instance, this cancels this one. You will also notice that L dot cosine squared and L dot sine squared will get added together. And with respect to these terms, you can again see that there will be an addition because you have a cosine squared and a sine squared, and the signs are negative in both, and therefore those two terms will also get added by using the trigonometric identity of sine squared plus cosine squared equals 1. But before we do that, let's process the other term, and that is the term which will have E theta as coefficient. So we go to the component in the I direction and multiply with minus sine theta plus alpha. So we'll have R cosine theta plus alpha times sine theta plus alpha, theta dot plus alpha dot, plus L sine squared theta plus alpha, alpha dot plus theta dot. We are multiplying by minus sine theta plus alpha, so just to keep that in mind, minus L dot cosine alpha plus theta sine alpha plus theta. I'm using alpha plus theta and theta plus alpha interchangeably, so please bear with me for that. Not that it is going to matter in this case. Then we take the component along the j direction, and in order to identify the component in the theta direction, what we need to do is multiply all the terms, each of them, with cosine alpha plus theta, so plus cosine alpha plus theta. So we'll have minus r sine theta plus alpha cosine of theta plus alpha, theta dot plus alpha dot, plus L cosine squared theta plus alpha, alpha dot plus theta dot, plus L dot sine theta plus alpha cosine theta plus alpha. So this square bracketed term will get multiplied by E theta, right? So here again we see that there are some cancellations. This term and this term cancels, and actually this term and this term cancels as well. So then the expression for Vp that we have is quite simply minus r, and we are going to add these two. So the cosine square and sine square are going to get added to give us 1. And let us now substitute for alpha dot plus theta dot, which is L dot over r plus capital omega. These two will also add up, so you'll get plus L dot. So this is in the ER direction, and here in the E theta direction you see you would have L times alpha dot plus theta dot, so plus L times L dot over R plus capital omega E theta. And so in the last step of simplification, one thing that you can see is there is a negative L dot here and there is a positive L dot here, so we'll get negative R omega ER plus L times L dot over R plus capital omega E theta. So that's our expression for Vp, and if you compare with the velocity expression in the previous page with method 1, you see that they match exactly. And so we have shown, and I'm going to skip the acceleration because it's quite trivial. You can proceed from here, either take this velocity in this expression and differentiate, which is exactly the same process as I did in the previous method. So essentially what we have done is we have shown two methods for direct differentiation to solve this problem that was solved earlier in Vdo17. Here we have solved it using direct differentiation, and two methods were adopted. The first used direct differentiation on a position vector which was expressed using a rotating reference frame. The second method, the position vector was expressed using fixed Cartesian reference frame. In both cases we were able to show that the values were the same once we had reduced everything to the same unit vectors, which shows that our methods are good, and direct differentiation is an alternate method to use of relative velocities. It depends on the problem as to what method you use. And so with practice you get a better understanding of which one to use given a problem. And that is the end of this video. We will stop here. Thank you.